you have a new tool, it's a lot of fun to use. But I think a lot of people are talking about accelerating science. I'm not necessarily skeptical that that's going to happen in some sense, but I think they're talking about it without trying to rigorously run tests as to how much the tools are accelerating things. So anytime I think about an open problem, the first thing I do is ask models for some ideas. They're almost always sort of nonsense. Never gotten an idea that sort of passes the sniff test for sort of a deep open problem. It's weird that we haven't seen a lot of mildly interesting conjectures resolved by AI. I guess we're now starting to see those, arguably. So I think right now, at least where I expect AI to have a significant impact is that the marginal cost of trying something is getting very small.
Hello, everyone. I'm Greg Burnham. I'm a researcher at Epoch AI, and this is my colleague.
I'm Anson. I'm also a researcher at Epoch AI.
And we're joined today by Daniel Litt. Hi, Daniel.
Hey, nice to see you guys and meet you in person. I'm Daniel Litt. I'm a professor at the University of Toronto in mathematics.
I wanted to start with sort of a fun one. Could you characterize, what's the hardest math problem that AI systems today can solve, however you might think about that?
That's a good question. Yeah, so I think, so of course there are these examples where now every frontier model basically has gotten a gold on the last IMO. And I think that's a pretty good baseline for what you should expect. So I think probably later in the discussion, we'll discuss a few open problems that have been resolved either with the help of AI or autonomously by AI. And I think it's probably accurate to say that those are about at the level of some kind of a mid-tier, low-tier IMO problem.
Gotcha.
I think there's some evidence that systems can do a little bit better than that right now. And I think, with some work, one can probably even elicit better performance than that from current gen models. But I think that's overall about the level of a contest problem, something you would expect a strong high school student or undergrad to solve in a couple hours. Seems to be about where the systems are at.
And one thing you've stuck your neck out on is that within the next year we might see mildly interesting conjectures resolved. Maybe you can say what that means.
So for me, I think what I mean by a mildly interesting conjecture is something that someone has stated in print. So at least one person was really interested in it. And hopefully someone has, spent at least a few hours thinking about it. I think there are a good number of problems at that level. I would expect that current gen systems can resolve some of these things with sort of the pass at 1 million or something like that.
Gotcha.
I think arguably some recent examples actually fit that bill. So maybe that prediction where I stuck my neck out has actually come true, although there's some questions about exactly,
how
interesting such problems are. Right.
Very nice. You've actually referred a couple of times already now to sort of time frame for human solve.
Yeah.
I was going to get around to that eventually. Is that a metric you like in general? I'm curious what you think about that.
To be honest, not really. I think that's not a great way to think about difficulty. So an IMO problem, a strong high school student, very strong high school student, the best students in the world, have about an hour and a half to solve the problem. That is definitely gives you some upper bound on difficulty. I think that for a lot of those problems, if you gave them to a professional mathematician, they would actually take longer.
Sure.
And that's just because, they'd fiddle around. They wouldn't be motivated in the same way as students in a contest. And also just solving a contest problem, there's a certain very constrained set of techniques you can use. And, in research mathematics, you're not constrained at all. So you don't just try the tricks and see what works. You try everything and you fiddle around and you maybe break out a computer and do some, work out some examples or whatever. So yeah, I think difficulty, it's sort of a funny thing. How do you judge it? And a lot of the times, maybe the best way to judge it is after the fact. So you look at the structure of the proof and you say, oh, well, actually, this wasn't that hard. Yeah. I think that's a little dangerous, right? Of course, when we're talking about evaluating a model, I think that leads to goalpost moving. The model comes up with a proof and you say, oh, well, that wasn't that hard. I didn't have to do anything. I just pressed a button.
One thing you've said often a lot on Twitter is that the amount of uplift that you get from these systems is actually quite limited. But then I think there are also some other people who feel like that the uplift is quite a lot bigger. I'm curious how you would characterize what the difference is, what's going on.
Yeah, I do think there's some areas where the models are just better. So, if you are working in optimization, for example, my sense is that there's a lot of people, for example, at OpenAI who are experts in that area and they've generated a lot of data and probably use their human expertise to guide the models. And So yeah, I would not be surprised if people, for example, in that area are getting more out of the models. Comparatively, my sense is that in algebraic geometry, number theory, the models are just not that good. I think also there are areas which are more amenable to sort of the tool use the models have access to. So, if you're trying to come up with a counterexample to some inequality or whatever, writing code is a very natural thing to do. If you're trying to come up with a counterexample to a conjecture about the intermediate Jacobian of a cubic threefold, probably there isn't really any code you can write that will help you.
That's interesting.
That said, I also think probably people are just misreporting the amount the models are helping them. You have a new tool; it's a lot of fun to use, but I think a lot of people are talking about accelerating science. I'm not necessarily skeptical that that's going to happen in some sense, but I think they're talking about it without trying to rigorously run tests as to how much the tools are accelerating things. I'm very happy to believe that some frictions are being removed, but there are also a lot of bottlenecks in research that I think the models just don't touch. And, so are you really accelerating if you, have removed a bottleneck to, opening a paper and finding lemma 3.7, but not to, having a good idea.
Yeah.
This is why we're glad to have you tell us what's right and what's wrong. Yeah. One thing I find interesting about that is like, the typical way I would characterize differences in capabilities or the spikiness of AI capabilities across domains is through something like Moravec's paradox. But then it seems like for things within math, like we also get this kind of spikiness within math. And I guess we were kind of alluding to some of this coming from what training data there is. Some of it is coming from like, what is more amenable to the AIs. Do you think like that's like explaining most of it? Do you think there's anything else like, or how we would characterize like the relative importance of these factors?
Yeah, I mean, what I do think is like doing research math is it's a skill that it's a little different from context math in that it's a very high dimensional skill. So it's not, there's not some more or less finite set of known techniques that are useful. I mean, okay, sometimes context math requires a little bit more creativity, but okay, to be honest, the models have not really succeeded solving problems where I think one can argue that's required. So yeah, I think a lot of the jaggedness we see in math, I think it's just the same jaggedness we see everywhere. I don't think there's anything special. Like, in my view, the biggest obstacle to the models like autonomously doing high quality math research is just the same as the biggest model to automating anything, which is like they can't do sort of long context tasks. Something that would take a human 6 months. There's just no task that takes a human 6 months that the models can do. So yeah, I think once we start seeing the models performing like software engineering tasks at that scale, I would not be surprised if they also start doing high quality math research. So I just actually don't think there's anything special about math in this regard.
Makes sense. Yeah.
Well, one sort of galaxy-brained take I have that I hold lightly is that models are weak in spatial reasoning, spatial intuition. That's not the galaxy brain part. The galaxy brain part is that is a big latent factor explaining what they're good and bad at. I do know from hearing narratives of various mathematicians about their thought process that often there is something quite spatial or geometrically intuitive about a reasoning process. And I do wonder a little if the AI models are especially good when there's a more symbol manipulation approach to solving something, coding being the most obvious, but even just working through algebra.
That might be. I to be honest, I'm a little bit skeptical of that kind of explanation. Like, first of all, there's a lot of diversity in how mathematicians think about mathematics. So some of us are whatever shape rotators.
Yeah.
Some of us are more like word cells or.
I was curious actually, trying to question this belief whether there are aphantasic mathematicians.
There are actually quite famously some even geometers who are
fascinating.
Yeah. Right now there's a huge number of mathematicians working on problems, and we have lots of different approaches, and that's partly why there are mathematicians who I think are overall, if you tried to put all mathematicians in line, way better than me at math. Nonetheless, I'm proving some theorems which they haven't proved or probably couldn't prove in the same amount of time. It's just because we have a different approach. So I think also, now there are like 3 or 4 models that can reasonably well solve math problems. They have slightly different approaches, a much smaller diversity of approaches than humans. And I think we actually see that reflected in the benchmarks. It seems like the set of problems that are being solved is like there's actually quite a lot of commonality between the models, is my understanding from hearing what you guys have been doing.
That's what our analysis shows.
Whereas, of course, all the problems in the benchmarks have been solved by at least one human.
So
I think, my sense is that you should think of the model as like a mathematician. And so there's certain problems that they'll be quite good at and certain problems that will be quite bad at. But maybe we shouldn't read too much into what those problems are. It's just an artifact of the fact that there's, only 2 or 3 models to look at to begin with.
Since you mentioned it, it's a big question that is very hard to answer, but I'm curious, how much transfer do you think we're seeing in capabilities across different subfields of math? So if you get this edge, surely you get an edge from generating synthetic data. How big an edge do you, as capabilities grow, do you not really need that? Or do you have any sense of this?
Yeah, it's a good question. I mean, I think it's sort of hard to say. My sense is that most of what happens when you try to get a model to prove a statement in algebraic geometry is that it tries to find it in literature or find something very close in literature and just try to maybe do 1 or 2 reasoning steps beyond that. It's really compared to what happens when you ask it sort of a combinatorics question. It's sort of not, at least in my observation, doing the same kind of real attempt to solve a problem.
Interesting.
And I think compared to a graduate student who maybe a graduate student who knows all the stuff the model knows about algebraic geometry or number theory or sort of fancy math topics would be able to do a lot more reasoning and really try to prove theorems. So it seems to me like the models are sort of superhuman in some mathematical subjects in terms of knowledge, but they don't somehow whatever reasoning capabilities they have or whatever they haven't necessarily learned the same techniques that a student who has that same knowledge base would know. This is just based on vibes.
Totally, of course, but I don't know. We've chosen you to hear your vibes. What areas do you have the sense the models are stronger in, native reasoning?
Yeah, at least I don't know about superhuman, but they're definitely super me at proving an inequality, for example, that kind of thing. My guess is just it's sort of easier to generate data, and there's probably a lot more data in that area than in algebraic geometry.
And when you say an inequality, are we talking contest style inequalities? Not something a little more interesting or important from analysis where everything's inequalities.
Something. Yeah, and so something where coding is useful. They're very typically very strong. Every once in a while I'll need to prove an inequality, and now my first step is just to sort of explore what the space looks like. By writing some code using a model.
I think we'll get into this a fair bit more, but you did mention 2 things I thought were maybe a little in tension. One is a thing that the models are missing is having a good idea, but another was if they can just do things for 6 months in many domains, maybe they'll be good in math as well. I say these are in tension because I think there are 6-month projects humans do that don't require having brilliant flashes of insight or anything particularly, planning a wedding or something, which models could not do today and takes months. Do you think creativity comes just with time, and so or I don't know. How do you?
Yeah, that's a good
relate
question.
these?
I mean, I agree that those two statements are kind of in tension. What I would say is I think there's some kind of continuum between just applying a technique and that's well known and developing a new technique.
Sure.
Arguably, a new technique is you take 100 different things and put them together in some way. Presumably. At least one ingredient to doing that is just time.
Sure, fair enough.
It's just not clear to me whether it's the only ingredient. I would say my experience of doing math is very rarely that I have a brilliant idea that just solves the problem. Of course, sometimes you wake up in the middle of the night and
I see
the problem is solved, but typically for that to happen, you have to marinate in the problem for 4 months. So there is some secret ingredient of time. I don't know that my introspection is well developed enough or trustworthy enough to say whether that's the only real ingredient. I mean, I think there are. Okay, let me amend that slightly. there are other things that happen, like you develop philosophies or analogies, and there's some kind of mystical aspect to doing mathematics that I think we haven't seen the models do, but it's also sort of BS, right? Like that mystical aspect of doing mathematics is maybe just kind of compressing a lot of sort of ideas that you've read or absorbed into some kind of package that's digestible to a human. So I don't know, maybe it's close to context compaction or something like
Interesting.
that.
Yeah. I guess there are these big analogies for like intelligence is search or intelligence is compression or something like that, and we're just better at that for now, and models have been getting better at it. And
I'm generally speaking, I'm also skeptical of those kinds of analogies, but like
say more.
I just think my sense is that there are a lot of ways to be good at math. Like if you just look at what different people are able to do, there's not that much overlap in capabilities. Like I don't know that there's any mathematician who like can prove the same theorems I'm proving, and there's plenty of mathematicians doing stuff where I think their way of thinking is just quite different from mine.
Oh, but I suppose, I mean, maybe I said this poorly, but if I think of, maybe it's not falsifiable, if I think of intelligence is search, then what that sounds to me like is you and a different mathematician are pursuing different heuristic search algorithms or something like that.
Sure, I think that there's maybe a way of making sense of it, but I would argue that's sort of not very contentful, right?
Sure.
Like if intelligence is some hugely high dimensional space and you just make a name for that space,
doing a good job at that is I don't know. You can't tell if it's enlightening or not. Could you contextualize the utility you're finding in the context of previous generations of tools? Like literature search is better, but Google Scholar existed, and that was presumably an improvement over card catalogs and conference proceedings.
Yeah, I mean, I think right now the tools are on a continuum with previous generations. So maybe in two ways. So first of all, literature search, definitely the models are now, at least for some literature search tests, better than Google or better than Google Scholar. That probably saves some time.
Sure.
Is it a lot of time? Well, I don't know. I mean, how much time does it save compared to going to the library? And probably a couple hours,
a bit,
every once in a while.
That kind of 2% productivity, long run productivity improvement, right on trend.
In general, I think that those improvements seem to typically be, as you're saying, like fairly small. I would be skeptical that this is more than 1% or 2%. For example.
Like if AI progress stalled today, you wouldn't expect that we already have baked in an explosion in quality of mathematics compared to what was developed 10 years ago.
Right. Yeah, I would expect a sort of similar productivity growth to what we've seen, which is maybe attributable to some extent to technology, probably mostly attributable to population growth. You can ask just the same question about Google, like how much did Google or email or that kind of thing.
I mean, did you live through that? Did that feel like, I don't know.
So, I was born in 1988, so I got my PhD in 2015. Google was already around by the time I started thinking about math. So I have actually asked older mathematicians this question. I think the general consensus, just self-reported, is that like Google did increase mathematical productivity, but it's pretty hard to see if you just like try to look.
Sure.
I mean, it's hard to come up with a proxy that lets you measure this, but I don't think it's obvious just from vibes, for example, that like the advent of Google led to like really, a remarkable growth in good new mathematical ideas. I just think literature search is not really where the bottleneck, the main bottleneck is.
That makes sense.
So there's another precursor to the development of these sort of AI tools, which is just the development of computing.
Sure.
So we saw a lot of progress in a lot of different areas, like in the, already in the 60s, 70s, 80s, just with the advent of computers. So for example, maybe a famous example is Euler had this famous conjecture, the sum of powers conjecture, which is, is there always a solution to a sum of kth powers being another kth power for some number of kth powers? I don't remember the exact number. So the first counterexample was found just via computer search. And then maybe more famously, the case of fourth powers was resolved by Elkies in 1988 using a sort of very clever computer search.
Gotcha. But like that method would have been dead in the water without computer search, even though there was a lot of cleverness.
Yeah, that's right. Yeah, so he sort of found a way to make these questions accessible to a 1988 computer.
Yeah.
I think probably now still they would not be accessible to just naive
brute force. Yeah,
but
that's fascinating.
But so this was a huge development. And I think in a lot of ways, like if we just stopped with existing models, we would see some kind of natural continuation of that trend.
What would that look like? I guess if right now we mostly use them for literature search and coding, maybe it's the coding aspect, like alpha evolve style thing. What do you think would be the developments we'd see?
So what I'm imagining here is, like sometimes to make progress in mathematics, you have to do a search.
Yep.
So like this Alke's example for this conjecture of Euler, and a lot of the time that search is sort of, there's some kind of art to it. Like maybe you're working it through 1,000 different examples and you don't have an algorithm to work through each example. So each example requires some little idea or executing some standard technique, but it's hard to write a computer program to do it. So maybe in algebraic geometry, you need to work through there's parts of it you can automate with a Python program, parts of it that require some real idea. So I think, probably where the models are now, you could imagine automating with relatively high reliability some of those kind of example searches.
That's cool. I see. So these are cases where it would have had to be, much of it would have had to be, or at least the amount of manual work scaled linearly with the size of problems. Now you could
some of that work can
cut that down.
So I think that's something that I'm really looking forward to. I think sometimes I'll write a paper which is just like, here's a beautiful construction.
Right.
And like to find it, I need to do some search and like kind of think about where the right place to look is. And, we already see alpha evolve is maybe some baby version of this. Where we kind of see some kind of automated search aided by a sort of clever LLM. I think that's something where I can imagine that having a really significant impact on mathematics. But I think it would be like sort of in the same spirit.
Yeah.
It wouldn't be an automation of mathematics. It would be a continuation
of figuring out how to use computers to reduce labor, open up new angles.
Yeah. If you think about, maybe the proof of the four-color theorem or Kepler's conjecture, that's a similar thing where you have many cases that one needs to check and you have a computer. You figure out how to get a computer to do that.
And I suppose you could get lots more of this if you just way amped up the compute. Like one question we ask about AI, because it's true all the time, is what's compute constrained?
Yeah.
Do you have a sense of, are some areas of math you could really get some fascinating things if you just gave them, 1,000 times as much compute as they have now? Or are these kind of hard to find, the little ones? I don't know.
Yeah, I mean, I think 1,000. Yeah, so people actually do this. So if you talk to computational number theorists, I've had actually really fun conversations where someone takes a problem and say, oh, well, this problem will be solved in this year just by taking Moore's law. Saying, when will it be no longer be compute constrained? And those predictions are reasonably accurate. So maybe about this example. Can you write an integer as a sum of 3 cubes?
Sure. Yeah.
So here we sort of know exactly how hard, at least conjecturally, each instance of this problem is. So you fix an integer, try to run it as write it as a sum of 3 cubes. We kind of know about how big to expect those cubes to be.
Yeah. I see.
But I think it's cool to do that for numbers where it's hard, but you double the computer, triple the computer, or multiple.
And you're not otherwise
you get a few more. Few more interesting integers, but there's a question as to what extent that constitutes progress. In my view, I think there are definitely people who are more excited about it than I am.
Fair enough. That makes sense.
Yeah, I'm imagining things where you're maybe looking for an example of some construction where there's not just a known algorithm that computes it, and you instead ask GBT to cleverly search and let it come up with ideas.
And if you give it enough test time compute,
maybe eventually it will come up with something. I'm just here. I'm not imagining it coming up with better and better ideas as the test time continues, but just trying more and more things.
Sure. And certainly if you had something like some way to verify, even if it's just more test time compute saying, does this idea look good or something like that?
Yeah.
Okay. And then I did want to just cover this. Are there problems that AI is causing right now? I mean, I think we know like cheating in college is clearly an issue. It's more tempting, lower bar to cheating sort of thing. Like what junk papers? I don't know. What's the state of this?
So I mean, there's definitely junk papers. So I think I started counting in maybe September of this year papers on the archive with the phrase Hodge conjecture in the title or abstract. So the Hodge conjecture is one of the 6 remaining open Millennium problems. It's the one that's probably, maybe the statement is the hardest to understand for a layperson. So for a long time, it was safe from cranks because you just like couldn't write anything comprehensible about it. So now that's no longer true. Of course, the frontier models can write, reasonable looking text about the Hodge conjecture. So I think in September and October of this year, there were something like 12 or 13 papers posted to archive, math.algebraic geometry, with Hodge conjecture in the title or abstract, and all but one of them were nonsense.
Wow.
And I mean, of course, I can't prove that they were generated by an LLM, but based on the writing style, it was quite clear. So to be fair, there were maybe 12 or so papers of this form.
Right.
That came from a smaller. The number of authors was not 12; it was maybe like 6 or something.
Oh, I see.
Like that. So
I see.
There were some repeat offenders.
Yeah.
But, so I mean, to what extent is this causing a problem? Well, it wasted several minutes of my time.
Right.
As the LLMs get better at writing coherent looking text, before you would have to spend 10 seconds to find nonsense. Now you have to spend a few minutes, actually. So like, I think the most serious offender here, the argument really did not make sense, but I really had to go to the middle of the paper and see that some statements were just nonsense. Like the introduction was totally reasonable and
interesting.
Yeah, and making some quite dramatic claims, which is why I was motivated to check that it was BS. But it wasn't a totally trivial job to do, and I think that problem will get harder.
Yeah.
So in particular in areas where formalization, like for example using Lean or other formalization software is not really practical right now, I think that's going to be an issue.
That's interesting.
And you can imagine way worse versions of that, which I'm sure are really happening, where a serious person, like maybe a graduate student who's stuck on a problem, uses one of these models to generate a nonsense proof of a lemma in the middle of their paper, where they, where maybe it doesn't make sense, and there, 99% of the proof of the paper is probably correct. It has no value because there's some nonsense.
Oh, that's an interesting case.
And that's very hard to catch. I mean, that of course already happens without.
You can. People have been bullshitting since time immemorial.
Yeah, there's lots of wrong papers out there, but a lot of this is about the marginal cost of doing something, and the marginal cost of lying and cheating is getting a lot lower.
Again, if capabilities froze, is this sort of at the level of society manages, because society generally, muddles through? Are there any things you'd be particularly worried about?
I mean, I think it's just contributing already to there's right now in mathematics, I think, a refereeing crisis. There's way more papers that are being generated than can be refereed carefully, and I think it would contribute to that. Probably it would continue to worsen.
Right.
A lot of that is about the incentives in math academia and not the models themselves. I think we'd manage the way we've been managing, but it's not
imperfectly.
I mean, I do think there's some hope here. Like, of course, the models can also be used to help check check papers, and I mean, there's already sort of nice tools that are being developed.
Yeah. So building on top of that, I want to think a bit longer term now.
Great.
A big part of all of this, progress in AI and math, is about compute and scaling, and one of the things that we discussed earlier was being able to, get the AIs to run lots of examples, help you work through lots of examples and do this kind of stuff. So I'm kind of curious, how we should expect the fields of math to evolve as we get more of this ability to run lots of experiments at scale. So I'm kind of thinking with previous numerical simulations, maybe that enabled, say, lots of simulations in meteorology and economics. What should I expect in the case of math, where we have systems that say are able to solve FrontierMath, and we're able to run lots of these models at the same time?
Yeah. So you're asking, just to make sure I understand, you're asking about the sort of thing I was proposing earlier, where you're just sort of working out lots of examples, not trying to get the models to solve through one hypothesis.
Exactly.
Like that. Yeah. So I think we'll see kind of a continuation of previous trends, coming with the advent of computers. We'll be able to work through larger volumes of interesting examples. Maybe, I don't know, I want to find an algebraic variety with properties X, Y, and Z. I can just have the model start trying things. The main benefit I think you get is the cost of trying the first dumb thing you would think of gets very low. Historically, if I want to find a construction, I have to sit down and try a few things. Even if doing that requires very little cleverness, it still takes a few days of my time, maybe. I'm a busy guy. Moreover, this might be just an idle question, and I have other things I'm more excited about. So there's some opportunity cost to doing these things. That opportunity cost, and also just the monetary cost of the marginal cost of trying something, will get very low, even if you're asking a model that's like not that capable to do it. That's very valuable. So yeah, I think one way mathematics moves forward is like you just like look for examples of cool stuff, and then like you just every once in a while you discover such examples. That doesn't necessarily require like deep insight or brilliance. It just requires spending some time. And so having automated search for cool stuff would be a really big deal. So I'm thinking about like, I don't know, there's some kind of sporadic examples of cool things, like the sporadic finite simple groups or the exceptional Lie groups, where of course people are searching for them in some kind of fairly principled way, but ultimately at some point you have to make a discovery, and that a lot of the time you just make that discovery by like noticing someone worked out a cool example, and then you like observe some interesting property of that example. That's happened to me. I mean, I think some of the projects I'm most proud of are like, I noticed something cool in the literature and then, like sort of drew some consequences out of that.
That's interesting. So that can be very productive.
Yeah, I think that can be very productive. I think it's a big part of how math moves forward. Like, it's not just that like, the most brilliant people are proving amazing theorems. Like there's a huge background of people like me who are, maybe more workmanlike, doing work and like just thinking about lots of cool stuff, and every once in a while they'll find something important. And I think that's something where just the ability to automate is probably a huge deal, even if the automation is not at the level of like even the median professional mathematician.
Sure.
That's I think the primary way I expect near term sort of mathematically capable models to make a big difference.
How quickly do the returns to running these kinds of experiments diminish? Like, I kind of imagine if I had loads and loads of these like AIs that are solving, like working through these examples, like maybe like 1,000 examples isn't really that much more helpful than 100. So like, would it be bounded? Really
I think
quickly?
it depends a little bit on how you're searching, right? So the most interesting examples are like, at least for me, is there's an infinite collection of objects and you're looking for 26 of them. Like they're really very special, exceptional things. So, a brute, it's not like you're doing a brute force.
Sure,
You're doing some cleverness, and the models can automate a little bit of cleverness. So I think that's I can imagine situations where being able to search through 1 million things is way more valuable than being able to search through 100 things.
And does that imply that like, or which particular fields will be most amenable to this?
I think everything. I mean,
everything.
I think there's lots of, I guess I'm thinking of algebraic geometry specifically, where there's certain sort of exceptional constructions I like. And, the famous example is this 27 lines on a cubic surface and 28 bitangents to a plane quartic and so on. And these examples have some interesting properties. Like they turn out to be connected in various ways to the exceptional Lie groups, for example. I mean, this is all known classically in the 1800s, but, it would be amazing to find, I think, this is sort of part of a series where there provably cannot be more examples, but it would be amazing to find like, new, cool, weird
things
constructions
like that.
Yeah, I think that's not something that seems impossible to me. People do regularly find sort of cool examples of the same nature, like weird phenomena.
Yeah.
Yeah. So it sounds like compute is like really important then. Then it sort of raises a question to me of like, why aren't all the mathematicians trying to go into like a big lab and working with like, OpenAI or DeepMind, or why aren't they going to places where there's a huge ton of compute and trying to like ride the wave and exploit it?
I think, to be honest, I think model capabilities are not really there yet, right? Like right now, the way you would try to automate this maybe is you just like run a model in a loop saying like, look for a cool example of this sort of phenomena. Like here are the examples you've looked at so far. When you try to ask the model to do a question like this, it will basically fail 100% of the time. So, I mean, I think, at least in algebraic geometry, just like the capabilities are not there yet. Like they just can't work through an interesting example. So maybe that'll happen soon. I don't know.
But we also think like if we extrapolate the trend on FrontierMath, then like maybe by the end of like next year, then it's probably going to be saturated. So like, should we be?
I think saturating FrontierMath is somehow not relevant to do this.
So let's maybe ask about timelines more just on the scales you care about. You made this bet with former Epochian Tamai Besarolu. I think it was, we looked this up, so I hope I'm getting this right. 3-to-1 odds that by early 2030, call it 4 or 5 years from now, time has progressed. So it's not 5, it was 5 years at the time of the bet, that an AI system would not be able to more or less autonomously produce a paper that would be publishable at today's standards in one of the top
in Annals,
which is like the top journal in your field. And so that was, if I'm not getting the arithmetic wrong, that's like you giving that a 25% chance.
That's right.
Of that happening.
Yeah, I think there's some chance I was overconfident. I think I probably revised my estimate more towards Tamai's side since then.
It sounds like, if I recall, Tamai, though maybe misreading from your perspective, the evidence was saying he was more confident, was less confident.
Yeah, I think actually, so Tamai has moved towards me, and I've moved towards him since.
It's beautiful.
Yeah, it's interesting. Yeah, it's not so clear to me. I mean, I think. Right. So this is something like, and there were a few more constraints. Maybe
sure. Yeah, please.
They're interesting. So first of all, it has to be repeatable capability. Although, of course, if the model proves the Riemann hypothesis, probably
we're past that. Yeah. But repeatable for the sake of there's not like a quirk.
It's not like it just finds one weird example that's a counterexample to some major open.
And everyone cares just enough. The stars align just right.
Regularly producing stuff. And then there was a cost constraint. So the marginal cost of had to be about $100,000, which was some kind of estimate of the marginal cost of getting a human mathematician to produce an Annals paper.
Sure.
So I've produced an Annals paper. Many other mathematicians produce Annals papers, and
you don't make millions a year, so
exactly. And I think that's a little bit hard to evaluate, like in the sense, like probably we're not going to spend $100,000 to compute trying to do this, although maybe
OpenAI will,
but maybe we expect the cost to drop. So if in 2031 it's doing it for $1,000, then
easy resolution.
Great. So sorry, what was the question?
Just sort of. Well, one good question here is, so first of all, 25, like just acknowledging 25% of this happening baseline in 5 years, like that's a lot of progress from where we are today.
I think that's very plausible as a forecast.
I mean, we could do a lot with that alone. Ask about what does math look like that. Sure. But I'm curious your updates since then, like why you might have moved in that direction.
I think 25% to me feels a little bit low. It's not really based on anything besides vibes. I actually think it's reasonably likely that models will be able to autonomously produce, very high quality research in that time. I think so that bet was supposed to be a proxy for will models have absolute advantage over humans in doing math research, and I think I've come to the view that it is a very poor proxy. Actually,
interesting.
And so one reason is the following. So right now there are mathematicians who I think are much more capable of, the marginal cost of having them produce an Annals paper is much lower than the marginal cost of me doing it. They're doing one a year. I do it. I've produced one Annals paper so far, and then a few other papers in comparable venues. Nonetheless, like, they're not like, they don't have absolute advantage over me in some sense, right? We have different points of view, and we're doing mathematics in different ways. So like there are areas where I have advantage, or there are areas where I have a substantial advantage in proving an interesting theorem, or understanding interesting mathematics, which I view as the actual goal.
So if I hear you correctly, it's like if models have 5 years from now the same characteristic they sort of seem to have today of they're all kind of doing the same thing. It's like a mathematician.
That's right. Yeah. So I think if you imagine, you can absolutely imagine models that are very strong at certain, even doing certain types of mathematics, or proving theorems of a certain shape, or even proving theorems of many, many different shapes.
Yeah.
But you would still maybe expect the fact that Maxim Kontsevich is around doesn't mean that there's no role for other mathematicians.
The cost criteria is relevant there a little, because let's just imagine that the cost was zero for this, and that we weren't at 200 tokens a second, which feels like a bizarre coincidence that we are sort of close to human speed of thought for models. I think of they're much faster than us at arithmetic. So putting those aside, which are totally real practical concerns.
So let's imagine we can instantly get some Annals papers.
And I guess my question is just, more almost from the human analogy, though, tell me if you think this isn't fruitful. If you put your own brain in a data center and could, run 100 subjective years in a minute, like, can you give every mathematician in the world a run for their money? Like maybe it takes you longer to do the sorts of things you're not so good at actually as a human, but that's a hidebound 2025 human perspective. What's the electronic version?
That's a good question. I think it's hard to say. So right now, because I'm limited in various ways, I mostly work in areas where I'm very good.
Yes.
And so, every once in a while that will involve like learning a new technique, or very frequently it will involve learning a new technique or developing a new technique, which is something I think the models have not yet really shown the capability of doing, which takes a lot of effort. I think if I was not so constrained, like I could start trying to learn other people's techniques more easily, and so that's a good question. But clearly, the answer depends a little bit on my capability of doing some kind of continual learning.
Sure.
So I think when we're comparing to a model, maybe it depends a little bit on how things develop in that direction. That said, my expectation is that no, I would probably do a lot of cool mathematics. I hope. It'd be very embarrassing if I was given so much resources and was not able to do it. But no, I think that it's quite clear that other mathematicians would still be very valuable. And there's certain sort of, I would say, styles of thinking or modes of thought within mathematics that I do not feel suited for. Like, maybe that's some kind of comparative advantage calculation.
I mean, this whole question, just to summarize it, is does AI break down comparative advantage dynamics that we're so familiar with?
Yeah, and I think I don't see a reason to think that. I think it's I mean, of course, we also ask the question without resource constraints, which is sort of somehow the key
critical.
Analyzing comparative
advantage. That's right.
A little hard to answer.
So this gives us a sense of what you sort of think 5 years from now might look like, where there's the math that the AI just happens not to be good at, humans gravitate toward that, and then a few humans are guiding the math that the AI is good at and building on it.
Yeah, and I imagine one would also try to automate systems and try to develop some kind of taste evaluation for the AI and try to get it to do interesting things on its own too. So I think that's a possibility. 5 years, maybe 25% is still around where I'm at. Sure. I would go a little higher. I think it's very likely, within 15 or 20 years that we'll have, there will be a lot of areas of mathematics where automated systems have advantages over humans. I would be surprised if that doesn't happen.
And this is a little our area, so I don't mean to unfairly ask you to do our job for us, but what is when you're saying 5, 15, 20, like what are you using to draw the trend line? Like vibes is a totally fine answer.
Primarily vibes. I mean, I do think I'm participating in the age-old tradition of AI forecasting where 5 years means you think it will happen soon, and more than 5 years means anything from 5 years to never. Years. Yeah. So I think that,
okay, fair enough.
There were a lot of people forecasting AI progress in the 60s and 70s, so I think we're saying 5 to 20 years in the same same way.
Whatever. There's sort of today, there's soonish, probably, maybe, I don't know, and there's like, oh, come on, who knows? And
but what I'm saying is I would be, I think it's 25% reasonably likely, but far from certain that if current trends continue, we'll see kind of high quality automated research.
So maybe we should see what happens when we go actually 15 or 20 years, or perhaps even more into the future. One thing I'm especially curious to get your take on is like the returns to scaling. And there's kind of like multiple dimensions that we could do this. So one dimension is kind of like what we were discussing of like thinking longer. Another one is like having many more researchers. And the last one is kind of like the scaling to intelligence. So maybe let's like start off with the first one. Is like, how do we compare like the scaling of like maybe one person thinking for 100 years as opposed to 100 people thinking for 1 year? And like, how much is there a way to characterize like how much better the person gets over the course of this 100 years?
That's a good question. I mean, so maybe let me kind of connect this to something we were discussing earlier, which is like how to decide how hard a problem is. So I think there are a lot of problems which clearly have the flavor of like, if you had a Manhattan Project to solve them, they would be solved pretty fast. Or like if you like the primary thing missing is attention, and if you somehow even got just a few some of them, even if you just got a few mathematicians to really devote a year of time onto them, like it's almost certain they would be solved. Like I think if you want me to name such problems, I probably can.
Sure. I mean, I'm curious.
So I have in mind, for example, we've discussed privately the inverse Galois problem for the last sporadic simple group. It's well known, the Mathieu group M23. I think that's probably a hard problem. A bunch of people have thought about it. I absolutely think that if we had the U.S. government devote, whatever the U.S. government spends $200 million on mathematics annually historically, although maybe less this year, we'll see. that if they devoted a substantial portion of that to solving that problem, it would get solved. I think
that's a good idea. That's helpful.
So that's maybe talking about just devoting some kind of resources, broadly speaking. So if you ask a single person to think for a long time, I think there are also a lot of problems where you sort of expect a solution. So maybe just as an example, there's a problem I started thinking about in maybe 2016. Like it sort of came up in a talk I saw, and I really liked it, and I tried to solve it, and I didn't really get anywhere at the time, but I kind of kept it in the back of my head, and then solved it in 2024. And so I think you learn stuff, you connect it to the sort of things you're thinking about. There's just some problem of like matching your knowledge to a conjecture, like knowing a conjecture even exists. So as you kind of just as time passes and you just try various things, sometimes you eventually hit on a solution. And here, in fact, part of the issue was like one of the ingredients of the solution just did not exist until 2023. So
fascinating.
Sometimes you just have to wait for someone else to do some work, and you realize it's relevant, and then
that makes the individual mathematician thinking actually sound a little bit more like a group of mathematicians because someone else did that other piece.
So some of it is just time passing. You learn things, you try different things, you become a better mathematician. Various ways you learn techniques. Also, a big part of mathematics, and I think this is something where humans still have a very substantial edge over the models, is like you have a new object and you try to make friends with it. Like you play around with it, work out various ask questions about it, to work out some examples and relevant special cases of the thing you're interested in. And I think this is something where you learn about an object that way and develop some theory for it. And this is something where I really worry about model capabilities in the current paradigm, and like trying to understand sort of marginal cost of progress, right? Like right now, for a model to learn about a new subject, or like to have a tool that has learned about a new subject, you have to train a new model. Right. Like, I don't know. So Peter Schultz is developing this theory of gestalten, which is some kind of new kind of space. And none of the models know about it. It's in some, I guess they can go online and look on the paper, but they don't
skimming it sort of level.
Yeah, they can't like take the object and like try to work with it. And make friends with it. So this is something that a human can do over time. And I think that's somehow the main way that time helps in solving a problem, is you kind of become friends with the object and develop some intuitions, and the models just can't do that without training an entirely new model. So they're the marginal cost of solving a problem that involves some kind of new object or new way of thinking is the cost of training a model. It's huge, like way worse than asking a human to try to understand the object.
So continual learning seems
very important
given for this.
And it's not just, it's somehow not just continual learning in the sense that I can read a paper and understand the object, but like at least if you expect the models to behave like a person, it's sort of playing. And I guess we have seen some attempts maybe at getting models to do some sort of self-play with mathematics, but not clear to me what kind of success that has had.
I mean, it's interesting that you can, I don't know, you see the chains of thought. And I feel like you certainly see glimmers of this, where they will try different things and play around a little and eventually hit on something, probably because it's what they've been trained to do, for the sake of solving a concrete problem, rather than this more taste-oriented thing of like, okay, I've got a better angle or a better grasp on this. It does feel like maybe that scales.
I'm not necessarily skeptical.
That's what it would take. Makes sense.
Yeah, I feel like the other part that I found really interesting about that was like, kind of like the limits to how much you can parallelize this, because like there was like this dependence from like another results in 2023, was it? And so like if we're comparing like the Daniel thinks for 100 years versus like 100 Daniels, like maybe like the 100 years thing is like probably more productive in the long run with the continual learning, but maybe there's also like a parallelization bottleneck, and like, or you need something else to happen broadly throughout the math economy or something.
Yeah, I think I think that's accurate, right? So like for example, in this case, this result took input from sort of two deep theories. So one was non-abelian Hodge theory, and the other was the Langland's program for function fields. And so the sort of main thing that happened that allowed this project to go through was someone else. So Ano and Groening had proven something using taking input from the Langland's program for function fields and the theory of companions, whatever that means. And I think that's not something I would have thought of. Like, it's okay, it's close enough to my area that I knew about it, and
knew how to
there's some
apply it
chance,
once
there's some chance I would have like thought about the question at least. But it's really a very creative and important development that was kind of different from different from the things I was thinking about. So I think it's really not clear. Like I would have even known it was relevant in some sense, like if I was just thinking about this problem for 100 years. I also think, historically, like asking a human to think about just one problem for a long time without, in isolation is probably not such a productive thing to do. Like you try a bunch of things, and at some point you start hitting diminishing marginal returns.
Right.
Yeah.
I guess the parallelization, it sounds like this is often the case. Diversification is important there.
Yeah.
And I guess today's models, have you tried to get them to do something surprising or more original, even if wrong?
To demonstrate creativity for sure. I mean, I would say right now, anytime I think about an open problem, the first thing I do is just ask the models for some ideas. They're almost always sort of nonsense. So I would say I've never gotten an idea that sort of passes the sniff test for sort of a deep open problem.
And so, I mean, it feels like random initialization in some abstract way should solve this problem, but we're just not seeing.
You can also try to, every day I wake up with a different random initialization.
That's right.
I think there's still, some kind of persistence in who I am,
biases.
Which limits my ability to really kind of search the full space of mathematics. And so, I
guess the other aspect of this was the returns to intelligence. So there was like comparing, I think if you had 1 million Ansons trying to do the stuff that you do, I think I would not make very much progress. And then if we're comparing, even if I like spend a lot of time trying to learn, like full time, just learn that. And then maybe like the next scale of this is like there's 1 million Daniels compared to super intelligent mathematicians. Like, would we expect this to have like the same kind of dynamic where like the super intelligence is just like so much better than even like no matter how many times you scale up the number or like the duration of our researchers, like just keep going up like all the way up?
Yeah. So let me first push back on the claim about you versus me, and then we'll talk about me versus. Okay. So I actually think I find it plausible that if you really devoted a long time to like learning cool mathematics, you would be able to do cool mathematics. Like probably it would be different math from what I'm doing, just because we have different preferences and different capabilities, we're stronger in different things. But I don't, you seem like a sharp guy. Like,
Oh, thank you.
Like I don't see a reason to think you wouldn't do interesting mathematics if you were sort of had the motivation and resources devoted to it. So similarly, I think with a super intelligent AI, if whatever that means, like, well, intelligence and even just within a fairly narrow domain of math research is an exceedingly high dimensional thing. Like we just see comparing different human mathematicians that were very good at very different things. And so I think even if you imagine an AI which is very, very capable of solving interesting research problems, it's not clear that it's very, very capable at solving all interesting research problems that all humans are good at.
But I suppose we could try to sharpen the question a little by saying whatever, Terence Tao is famous, but but you've mentioned others as perhaps in other fields, whose name is Schulze, I guess.
Schulze and Kontsevich or something.
Exactly. So within whatever net you want to cast for people who are well suited by interest or disposition to a particular field, like what do we observe in?
There's still huge differences, right? So like,
it's so high dimensional.
Maybe an example is there's a sort of classical dichotomy even within any field is that of theory builders versus problem solvers. And I think that's in large part about interest, but also about capability. Like I think of myself maybe as more of a problem solver than a theory builder, and I think part of that is just like I'm not as good at theory building. Like sometimes I have to do it in order to solve a problem, but like there's partly what I'm good at, and partly like I enjoy trying to solve interesting problems. But I think that's also, even that shade is like some kind of continuum, or maybe high dimensional continuum. Like some problems are like develop a theory to do this.
Well, I still feel like we could sharpen this because you just say, okay, so add whatever dimensions you want, and now we see a spectrum of
of you can absolutely, of course, imagine an AI which exceeds human capability in every dimension.
Yeah, I guess what I'm curious about is whether, just from human evidence, do we see? I have in the back of my mind, I should just say it, this kind of lighthearted quote by I think Pfefferman on when Tao got his Fields Medal, saying like, everyone, if you get stuck on a problem, the surest way out is to interest Terence Tao,
Right.
suggesting sort of that there was the sense of, like if you get a more capable human on a problem that they're a good fit for, like that isn't a theory building problem or whatever project for a theory builder in an area that they're interested in or something like that. Like, do you have? I don't know.
I think that they're a good fit for is the key there, though, right? Like, I think this may be a matter of expertise rather than capability, but like, I think if I got Tao interested in one of my problems, it probably wouldn't be that helpful in the near term. Like, maybe he would load up a huge amount of algebraic geometry or arithmetic geometry into his brain, and then that would be helpful. But, that would take a while.
And I guess the question is just for whoever is most is smartest subject to being a good fit, for lack of more nuanced terms. Whether that, like, just what that scale of productivity looks like. I don't know, there are people who you avoid working on that problem if they're working on it because you're like, oh, surely they're going to crack this before I do.
I would say that happens in some sense, but I don't think of it as about capabilities. It's like, for example, there's a very active area now is p-adic Hodge theory. I, am adjacent to it in various ways. I consume the output of p-adic Hodge theory. I don't really work in the area. But it's just because it's a very fast-moving area, and like if I wanted to get into it, I would have to learn a lot and then catch up to these people who are working very quickly.
Got it.
So it's more about opportunity cost than capability.
Okay, so we don't see so much like the return to whatever we call intelligence in humans. It's not.
I mean, I have a 2.5-year-old who I think is very sweet and very sharp, but she's not
so good at math
doing math research right now. She's 2.5. So there are absolutely differences in capability between people. But I think among professional mathematicians, it seems to me mostly about the fact that it's a high-dimensional space and people are interested in and specialize in different parts of that space, even within sort of fields you feel are kind of narrow.
Yeah.
Maybe a remark on that is like, I think, so if if models kind of continue in the current paradigm where they are kind of very jagged and have, in some sense, sort of narrow capabilities compared to a person, even if that happens, you can still imagine some kind of very substantial value, just because the fact that we specialize in these sort of tiny little zones in a very high dimensional space means that basically all problems are kind of attention bottlenecked. The number of people who even knows what the words in the problem statement mean is like 10. And you can imagine that in some sense those problems are not very difficult because of Moravec's paradox. They're just like no one has really had time to think about them.
I guess like another way of kind of thinking about this in the way that like say to people who care about super intelligence and like fast AI takeoffs and whatever is like, suppose we increase the rate of math progress by a certain amount based on some measure that we think is most people agree is reasonable. And then we try to break this down into like, because we have these like 15 to 20 years in the future AIs that are doing the math research, and we break it down into like the 3 factors that we were talking about. It's like more AIs thinking for longer, and like smarter AIs.
Sure.
Like what would do we have like a sense of like what the breakdown would be?
That's a good question. I mean, my sense is that it's not clear to me to what extent like progress in math research has increased over the last 40 years or whatever, let's say prior to AI, but maybe my sense is that productivity growth, like total productivity growth, comes down largely to the increased number of mathematicians. So, maybe once you expect AI to reach a certain level of capability, I like at parity with humans, if this happens, maybe you expect it to come down to number. A little bit of a concern there is like why are there returns to numbers of humans? I think a part of it is just attention. Part of it is like there's diversity of modes of thought, and maybe you don't have as much of that with AIs, depending on how systems develop. So I don't know, but I do think probably a lot of the returns to increased number of mathematicians just comes from increased time spent thinking about different problems, increased attention, and that I expect you could see substantial returns to even with sort of not very capable AI. So what about returns to intelligence or whatever? Again, I think this is sort of not such a well-posed problem. Like I think it's a very high dimensional, like intelligence is sort of a very high dimensional object in my view. But yeah, I mean, so okay, maybe let's call it something like the ability to, search through some, high dimensional space of proofs in a clever way, I guess you can imagine that being very valuable. Like, presumably the proof of the Riemann hypothesis will involve developing various objects and theories that don't yet exist, and that would, take a lot of, you'd have to search for them in some very high dimensional search space. But I don't know. It feels sort of like too much speculation. Like I don't know. Yeah. Like in fact, I think a lot of the way that search happens in practice is like that people who are just normal mathematicians are sort of just thinking about objects and observing, like doing this sort of low-level search I was discussing, like working through lots of examples and notice patterns, and then people start to sort of encapsulate those patterns into the relevant objects and like I think somehow that sort of high-level theory building, which we attribute to maybe the most brilliant mathematicians, really depends on sort of a background of just like hard work and example analysis.
Mm-hmm.
So arguably some of that is also attributable to just scale and the number of mathematicians and the number of sort of questions people have thought about.
As a fun little, just what are your solve probabilities over time for the Riemann hypothesis, or pick your Millennium problem if that's not your...
Yeah, so okay, I mean, the ones I'm probably most familiar with are Riemann hypothesis, Burton, Swinnerton, and Dyer, and the Hodge conjecture.
Mm-hmm.
I think of those, the Riemann hypothesis actually is the one where in some sense we know what a proof should look like.
Uh-huh.
And the reason why is that there's an analogous conjecture, the Weil conjectures, which is the Riemann hypothesis for varieties. Well, part of it is the Riemann hypothesis for varieties over finite fields.
Mm-hmm.
That was proven by Deligne in the 70s. And maybe the part that's most closely analogous to the Riemann hypothesis is the Weil conjectures for curves, which were proven by Weil much earlier.
Yeah.
So we really have some sense of like what the shape of a proof should look like. It should look like Weil's proof.
He
gave two proofs, but one of Weil's proofs of the Riemann hypothesis for curves.
Mm-hmm.
And then the problem is that there's various maneuvers one makes in that proof that don't make sense for like the integers rather than a curve over a finite field. And so one has to figure out how to make those maneuvers work. I mean, this is sort of science fiction, but I think this is at least some kind of plausible, mystical way of thinking about a proof. So yeah, of course, many mathematicians have thought about how to try to make these maneuvers work. And I think there's some chance that, one of those attempts will work out in the next 10 years. I don't know. I mean, it's the number I put on it is like 15% or something.
Gotcha.
But that's just meant to be like a fairly small, but not
sure,
zero.
Small but not zero.
Yeah. And in general, I think if you look at like sort of solutions to major open problems, like the time difference between the sort of last big idea you need and like completing the proof has been fairly small. Like, for Maslow's theorem, like the distance between the Taniyama-Shimura conjecture, which is sort of a very hard conjecture related to the Langlands program, and the proof of the Riemann hypothesis, not
the
temporally not so long. Sorry, for Maslow's theorem, it's not so long.
That does make it sound a little like maybe because Weil conjectures for curves is decades old. That maybe
so in fact people expected, I think, when Deligne proved the Weil conjectures, that the proof of the Riemann hypothesis would come soon. That's this is well before I was born, but that's my understanding of the history. And then it wasn't.
So maybe some other
so people don't know. So I think people don't really know what the missing new ideas are. We have some sort of very vague senses to what their shape should be.
And then I guess the obvious follow-on is what has your prediction time frame changed with AI progress at all?
That's a good question. I mean, I think I am right now. I haven't really I don't feel like I've. So part of the reason of my bet with Kamai earlier is that I don't feel like I've seen some aspects of what I think is necessary for high quality research.
Got it.
I don't think I've seen sparks of it from AI. The distance between solving an IMO problem and doing high quality math research is larger in my view than I think some other people seem to think it is. Yeah, I would say it has not moved so much. I mean, right now the tasks that AI can help with and the tasks it seems like it will soon be able to help with don't seem to me to be the primary bottlenecks for resolving major open conjectures. That said, I do think, I gave a 25% chance that that these problems will be solved and AI will be able to, resolve, do high quality research. I think depending on there's maybe some 5% of that, there's some, depending on how that works, it could be
so good that it's on track to do something, crazy. Yeah. So just for fun, Millennium Prize problems, these big targets in math. I can't tell, where are you on how likely you think those will be solved and whether AI will contribute substantially to those solutions.
Yeah, I mean, I think my median prediction is that 0 will be solved autonomously by an AI in the next 10 years.
10 years?
Yeah.
I see.
At all, I would say maybe 0 to 1, I would expect to be solved in the next 10 years. You know, there's arguably been some progress on Navier-Stokes, which is far from my area, but I don't find it totally implausible that that will be resolved. And the current news about it is about a team working jointly with DeepMind.
Yeah.
That would be with some kind of maybe more traditional deep learning techniques involved, not LLMs or reasoning models.
And I guess one of the 7 was resolved not too long after they were codified, the Poincare conjectures. So our base rate is not 0. We shouldn't expect these are impossible. They're just very hard.
Yeah. But I think with a couple of them, like Hodge conjecture, seems like there's just no ideas.
I see.
BSD similar.
Yep.
With the Riemann hypothesis, I guess we discussed.
We mentioned,
There's some kind of ideas, but it's really kind of unclear how far we are away. I think it could happen in the next 10 years. It could happen in the next 100 years.
And so relating this to your other AI timeline senses, the 25% chance that we do hit annals level papers in 5 years, some part of that goes toward,
I think it's, but my expectation is that it seems very possible for that to happen without starting to knock out Millennium Prize.
Basically not much of that. Yeah. And then you're sort of like 20 years. Yeah, you're it's beyond the when this all has had a lot more time to brew and develop.
Yeah. And I think it depends a little bit on what kind of, we talked a little bit about acceleration. I'm not an expert in this, but presumably there's some question about acceleration of AI progress itself or self-improvement. And that I'm generally pretty skeptical on.
Yeah.
In the same way I'm skeptical of acceleration in general.
Yep.
But we'll see, I guess.
So, and this might slowly transition us into measurement, benchmarking. But first, with sort of a fun speculative version of that, you've said you're not seeing so many glimmers of some of the things you think are critical. Yeah. Well, let me ask the boring version first. What are some of those things? You've talked about them plenty on Twitter, but just for our sake here, what are some of those?
Yeah, so let me imagine, like what are some things that would be signs for me? That,
sure. Yeah. That's the fun version.
Like, for example, making a new interesting definition would be important. So showing some kind of research taste would be important. So like asking a question or like discovering even just like conjecturally some new phenomenon. Like I think a lot of the most important mathematics is actually just making conjectures.
Yeah.
It's sort of hard to get current systems to do. I think it would be interesting to do experiments there. Developing this is sort of related to making a definition, but some kind of theory building. I don't think we've really seen. Like somehow it's already been very surprising to me that the models are able to learn during training. I don't mean during use or during deployment, and like techniques that please apply them. So that I think that's somehow the thing that really changed with the advent of reasoning models. Like they were able to take some sort of well-known techniques and now start to really apply them with high reliability to do math. If they were to, this is sort of a fuzzy thing, but if they were to develop a new technique, this is, there's some kind of continuum between old techniques and new techniques. Like you put a little twist on a new technique, on an old technique. Is that a new technique? But if I were to recognize something like that, that would be a sign. And I don't think any of those things have happened. Will they happen soon? Maybe. No.
And just in case it catches anything else in the net, if I were to say of the tasks that constitute doing math, which are the hardest for AI systems, this kind of theory building, conjecturing category seems critical. Are there others you might put in?
I mean, right. So like for me, I tried to have all of my papers contain a new idea. And again, this is a fuzzy thing, new idea, new technique, whatever. It's not true for all of them. Sometimes you find a trick to resolve some old conjecture, and of course,
worth writing it
down. I think that is, most people don't have a lot of new ideas. Like as mathematicians, I think typically write, depending a little on the area, but 1 to 2 papers a year. So compared to other subjects, we're not very productive in terms of total output. And I think that thing where you develop a new technique that's really or a new sort of genuine new idea. I mean, what does that even mean? But
I know it when you see it.
That's the hard part.
Yeah. And so I think we've practically answered it already, but with something people like to point at for the game playing systems, Go in particular, AlphaGo was a Move 37. Yeah. I suppose something like, I think part of what was exciting about Move 37 is it was described as an inhuman move, like a move no human would have thought of. And so the AI had really stepped out of the bounds of, I mean, it wasn't trained on much human data, but it had stepped outside the search space that humans had looked at.
Right.
It sounds like it would be enough of a Move 37 to just have a new idea, even if it was something a human could think of. I don't know.
It's kind of funny. I mean, in some sense, that's happened prior to the deployment of these AI systems. Like if you think about, the proof of the Kepler conjecture, proof of the four-color theorem, like those are inhuman proofs. Like they're of course, a human was in charge, but the sort of the majority of the work was some kind of horrible casework done by a computer, or beautiful casework. Sorry,
of course,
no such thing.
Does anyone
think it's horrible? No, I'm not. I like to say in mathematics that everything true is beautiful.
Yes, so, and you've said you encourage your grad students to adapt their way of thinking to this.
You should prove things by any means necessary.
Totally.
Why tie your hands behind your back? So that's some kind of Move 37, arguably, right, which had nothing to do with an AI system. Would I consider an AI system generating that kind of proof, so like automating a huge amount of casework itself, to be a Move 37? No, because we've already seen humans do it. I guess you can also imagine some kind of weird like lean proof of some hard theorem where with no comments, that itself is very hard to extract a human argument from. Like if you've ever looked at lean code, it's not easy.
Junky.
Tough. So I think if I were to see something that I considered to be like a new technique, like something where I couldn't really find a precursor in literature, I mean, well, whatever, again, it's sort of a judgment call as to what a precursor is, that it would be very exciting.
And I mean, this is part of why I pay attention to your commentary, is I think that like goalpost moving, post hoc judgment, very hard, but you seem to be trying to do an honest job.
I should say there's a huge temptation to build posts here. Like, maybe if I do think to some extent it's fair. Like right now, the signal you get from AI solving a problem is partly the AI is capable and partly the problem is easy.
Yep.
And so, mathematicians have a habit of saying, oh, this problem was solved by AI, but it was actually easy. So maybe we shouldn't update on that.
Right.
And to some extent, that's true.
Of course.
I think
should be a mix. Yeah.
Yeah. I think, we should try to evaluate what the models are doing and try to see like, oh, well, if a human had written this, like, would I be excited? And I think that's what I try to keep in the back of my head here. Like, so for example, for these recent Erdős problems, like if a human told me they solved this Erdős problem with this proof, which has happened, I would be like, oh, that's cool.
Yeah.
And that's also how I feel about the AI.
Right.
Oh, that's cool.
Yeah. And like life goes on, but don't diminish it in the moment. Yeah, good. You did a thing. Yeah. Did something nice there.
Yeah. I'm curious if you think it's like feasible to actually, let me step back a bit. So one thing you've mentioned on Twitter is like that whether these problems are like solving these problems is impressive depends a lot on whether or not there was a lot of human effort that was put into it previously. And do you think it's possible for us to kind of like say go through these like Erdős problems and then kind of like just, or has it already been done? Like just to try to like say how much
them on
how much effort has been put into it.
Of course, you can kind of look at, they were proposed in some paper. You can look at how many citations that paper has. I think with the ones that were solved, I actually don't know. So I think the hard version of 124 that was not solved, the paper has 14 citations. So for a 1996 paper, that's math is not a lot of citations.
I see.
So
I don't know the baseline here.
14 is not a lot, but it's not
nothing.
There are plenty of papers from 1996 with 0 citations.
Of course, this might be a long paper, so it's unclear. It's cited.
It's a 6-page paper, but it's probably it has a lot of problems in it. So I think it's probably many of those probably are not citations
to the problem of interest.
I would not. I haven't gone through them, but I would not be surprised.
Do you know how many people are working on the p curvature conjecture?
Very few, I would say. I mean, but it's something where. Yeah, so for context, the p curvature conjecture is kind of the Grothendieck-Katz p curvature conjecture is kind of one of my white whales. It's something like I've thought about a lot. I think probably very few people are actively working on it. I assume I would expect I know all of them. Probably it's fewer than 20 is what I would guess. Historically, there have been more. So I think there was quite a lot of activity in the 80s and 90s and early 2000s, and then somehow people got stuck and it died down, and maybe now there's some new ideas again.
Gotcha.
Or at least new ideas in related areas. But yeah, I think it's somehow any question where the words involved, not a lot of people know what they mean, is automatically going to be attention bottleneck.
Small denominator.
So, yeah, like here there's probably a couple thousand people who know what all the words mean.
Gotcha.
Yeah.
Is there this is a little random, I'm just curious, like, is there a bit of a selection effect where, I know with the Collatz conjecture, there Wikipedia discusses how it's a little embarrassing to work on. So because that's how it's characterized.
It's also kind of a crank magnet, I think.
That too, maybe. And so you don't want the association with that. Yeah. But also, I guess there's some problems where it's like, who are you, famous open problems like this, where the expert opinion is we don't really have the right techniques to solve it. And so there's a little bit of a like, I don't want to stick my neck out and say, I think I'm good enough to. Are there a lot of quiet, small attempts on big famous problems that wouldn't be announced? Like, is there a silent 10x population?
I think probably everyone, thinks a little bit about a big problem. It's hard to make an attempt on a problem like that. Like you need an idea. And I think with the Collatz conjecture, I think many people actually have thought about it, including quite well-known people have published papers on the Collatz related topics. So I think it's not really attention bottlenecked.
Sure, but I more meant if you were trying to estimate the amount of attention it had received, would you have how would you account for the fact that probably everyone has thought about it.
Right. So what does it mean to try to solve a problem?
Exactly.
A lot of the time, you're like, oh, it would be nice to solve this problem. And then, you try nothing.
Right.
So how many people actually try something?
Or maybe a different angle is what does it feel like when you're like, oh, maybe I do have an idea worth trying. Of course, it mostly fails most of the time, but not just, I remember the Riemann hypothesis today. Oh, well, that was nice. More like, oh, what if this has some bearing on, what is that? How does that come about? It might just be.
So usually sometimes you wake up in the middle of the night. Great idea. That does happen. Sometimes a lot of what I do when I try to think about a problem I'm interested in is, either you start with an idea, you start with a new technique that you kind of came up with in some other way, and you're trying to extract value out of it. So you kind of think, what problems is this relevant to? And some things, so that's sort of an opportunistic approach to mathematics. What happens sometimes for me, and sometimes I do kind of set out to solve a problem or prove something, or maybe more accurately try to understand something and then benchmark my understanding by proving something related to it. Is you kind of take the minimal example where you don't know how to approach it via the techniques that you have available to you, and you try to work it out and develop techniques to handle that minimal example, and then you see how far those.
You maybe get a little hill climbing effect going on.
Yeah, and then of course you can iterate that. So I think So the most common, I think, situations for me are either somehow kind of opportunistic approach to a problem. And I think this is, by the way, something where AIs can be, I expect, kind of helpful, right? In order to resolve conjecture, you have to know it exists. And so you develop some technique, and then you can say, well, what is this relevant to? I think.
Does anyone else care about this?
So far this hasn't been useful, but I have resolved open conjectures by developing some technique, and then someone mentions to me, oh, is that related to this? And then I'm like, oh yeah, it is. And then that, solves in some example, solves a 40-year-old open problem. That can
very nice.
So one possibility is opportunistic, and then the other one is the situation where you're kind of try to extract some minimal viable example and just play with it until you get somewhere.
I guess this, from a data analysis perspective, part of what is in the back of my mind is if we do take something like what Anson suggested based on citations or whatever as a metric, would there be something kind of nonlinear correction would there be some kind of nonlinear correction we need to do for, but that's going to understate famous problems because everyone sort of checks, I have a new technique.
Understate or overstate? I mean, I think there are a lot of papers that cite the Riemann, work on the Riemann hypothesis without making any meaningful progress towards the Riemann hypothesis. It's not so clear.
Great, then it's a wash.
I think it's very hard to evaluate difficulty this way.
I guess there's also the junk papers problem, or
the rigorous
suddenly
proof more famous.
The Riemann hypothesis.
Oh yeah, there's also a huge number of papers claiming to prove the Riemann hypothesis, which obviously make no problem. Yeah, I don't know. Probably there's a huge number of computer science papers citing things relevant to P versus NP. Are they really making progress on it? Like how many people are actively thinking about P versus NP? So, yeah.
Linear approximation it is. Yeah. We'll get by. Before we move on fully to measurement, I remembered one other question for you, which is I think you have a clear-headed view on AI, where it's going, where it might be going, reasonable probabilities, whatever, non-extreme anyway. Have you made, or are you starting to plan ways you adapt your own professional life or trajectory to be, survive in this world, thrive in this world?
Yeah. So I would say there's certain things I'm doing with the expectation that AI will become more capable. So for example, right now there's a lot of work on formalizing mathematics, like in Lean or other proof verification software. And I'm not really working on this. And the reason why is that I expect that tools for vibe coding
vibe formalizing
will dramatically improve over the next few years.
Got it.
I mean,
just
probably it's faster just to
catch
wait
up
for
with
better
you.
tools than to try to do it myself. But partly this is because I'm not very good at it.
Sure.
I'm not an expert in Lean. I play around with it a little bit. So that's something I'm doing differently. I don't think I'm adapting like which problems I think about or what techniques I'm using based on the expectation of improved capabilities. And I think part of the reason why is that I just don't view my job as like proving things. I view my job as like trying to understand things.
Yeah.
And then when you prove a theorem, that's like a benchmark of understanding. So that's like,
gotcha.
There's some theorems that are interesting because, or conjecture that sort of helps you understand a subject, and then proving it actually is it improves your understanding of the subject. But often, a lot of theorems or conjectures are kind of sinks rather than sources. Meaning, if you've developed a technique that can prove the theorem, it shows you've understood something, but the actual value is in the understanding. And it's sort of funny. I think this is maybe something that explains part of the difficulty in training AI to do good mathematics, which is that a lot of what we write does a poor job of conveying the actual value proposition of mathematics, which is that there's a human who now understands this object better.
And like what the words in your mind, in the voice in your head that like, amount to or sort of are tightly related to that understanding is not the words that appear in the paper.
Right. And of course you wish you try to convey your intuitions, but it's just a famously hard problem. Like, if I could tell my students like, oh, like this is how you should think about this object. I mean, of course I do tell them that,
right.
But like it doesn't convey anything valuable. Like it gives them some hint that they can kind of decompress or unpack in some way by playing with the objects themselves. But you can't directly transmit that understanding. It's just not contained in the text except in some very compressed or hinted at form.
I can also imagine like you write up a paper that's here's the proof of this conjecture, and the route is so much more roundabout to developing that theory that there's just not much training.
Yeah. I mean, a lot of work is like, in fact, when you prove something, you have some often very straightforward idea for how the proof should go, and then there's various roadblocks that come up, maybe because we don't understand some intermediate object in the proof, and so you find some way around it, and the actual written argument looks very ugly. And of course, you try to hint at like this is what I'm actually trying to do, but how successful is that? Right. So how is this related to like how AI affects at least my personal planning?
Yeah.
Right. Like, AI can't understand something for me.
Right.
Right. And because of this issue of the difficulty of conveying intuition, like even if a model exceeded my capabilities in every dimension,
right,
like that would probably help me a little bit understanding these objects. But
you'd have
maybe not as
you
much
got
as
stuck, but you'd still have to do the work.
Like, you still have to do the work.
I mean, I saw you say this on Twitter, and I think you were citing a mathy philosopher, Pellegritzer, on like the point oddly enough, the societal role for a mathematician is to embody mathematical understanding.
Yeah, I love this.
It's beautiful. What a nice. Actually, I can't tell how much he is bothered by this. If we're in a world where, but I'm curious how much you're bothered by it or not. If we're in a world where AI systems can pretty quickly resolve any faster than any human, total AI dominance of human mathematics, would we still would that bother you? Would you still pursue mathematical
I mean, I think there's
understanding?
like some kind of, part of doing math is like you get a rush when you prove something that's fun. That thing doesn't necessarily have to be open to an open problem to get that rush, actually.
Yep.
So, you lose maybe some ego boost or whatever, but the main sort of emotional aspect is still there. But also, I mean, like for me, I think the actual goal is to understand stuff in a world in which like our primary role is to, as Pelly likes to say, embody human understanding, or where we're running seminars on the latest great result proven by an AI.
Yeah.
Like if society is willing to support that activity, I would be pretty happy with it. Like
this lasts in post scarcity utopia.
For sure. Yeah, and I think I mean, just to be clear, I do think we're quite far.
Sure. That's at least a question that isn't, in some ways, isn't super duper speculative, because who knows how long it takes to get there. But if we're still like ourselves when we get there, then we would want to do that.
Yeah, there is of course like a social question, like if models have absolute advantage over humans in all areas of math research, or if the public has the perception that they do, which I think is more likely, will society be willing to support that activity? I think that's an open question. But I hope so.
Sure. Somehow it's lasted. I guess maybe society currently has the perception that math ends up being useful like a lot of the
which
time.
Is sometimes true.
Sometimes true. Yeah.
Sometimes true. Yeah. I mean, I think overall, one way in which math does end up being useful is that there are human experts, and that there's human capital developed out of math. So even people working on the most abstract and pure mathematics, like the fact that they embody understanding is valuable. And it's not totally clear. I mean, I think depending on how creative and sort of capable of innovation the future models are, it may still be valuable to have humans embody that understanding, even if it sort of narrowly within math research, AIs have absolute advantage.
We would love to take like the track we've been on, making benchmarks, FrontierMath in particular being, the work Epoch has done in this, and like continue the y-axis up,
right.
Because but it seems like that would be maybe a little naive, because I think as we've learned from making FrontierMath, like that y-axis is not capturing everything that's important. Right. So first of all, just to get it on the table, what is the big thing? What are the big things that's missing?
Right. So let me kind of say a little bit about what I think a benchmark measures. Yeah. Maybe and then we can say what's left over, right? Yeah. So I think maybe what you're trying to do when you make a math benchmark is you're trying to benchmark to some extent knowledge. Like, do you know what the words mean? Do you know what the existing results are? Knowledge of existing techniques. Can you apply existing techniques? And then also some kind of reasoning ability and creativity. Like some problems are supposed to be hard, which means that they require some kind of reasoning ability. And I think what the benchmarks primarily end up measuring is knowledge. Yeah. And so let me kind of dig into that. So when a human solves a problem, humans typically have very limited knowledge. So what do? They maybe have some idea, and then you work on it for a while, and you realize, oh, I need this fact, or I need this result as an intermediate step. And then you try to prove that result, or you look it up, or whatever. But the activity of like proving an intermediate result is like a very or even finding that intermediate result, realizing that it's something that could exist, could be true, is like a very reasoning intensive activity. If you have memorized the entire mathematic literature, you already know that result exists. It's much less reasoning is required to realize that it's like a true fact that would be useful to prove the thing you're trying to prove, or compute the object you're trying to compute. So when you're asking a question to something that has memorized the whole literature, I think what you're primarily doing is like, you're not testing that sort of secret reasoning ability that happens when a human who with very limited knowledge tries to solve a problem. Like they have to find what knowledge they need they have to discover something intermediate that is already discovered by someone else, but not by the human in question, and the model already knows. So I think a lot of questions that in humans test reasoning ability and are correlated, very highly with mathematical expertise and research success are much less correlated with that kind of capability in models, it seems like. Yeah. I mean, models, I like any human who can do as well as a model can on FrontierMath, like maybe no such human in fact exists. Right. would probably be a very successful researcher, a reasonably successful researcher in a way we're not seeing the models do. And I think this is part of the explanation. The models, the very same question is testing something different in the models than it tests in a human, because the models sort of require much less reasoning ability to sort of find the intermediate results that they need.
To add something you may not have seen, because we did this deep dive into Gemini 2.5 Deep Think, its math capabilities, including running it manually on FrontierMath in the web app. The FrontierMath questions, the problems, all have 3 ratings associated with them, which we called background, execution, and creativity. Execution was sort of something like, how long is the solution? Just how much like nitpicky calculations do you have to work through? Background was how advanced and obscure is the background, and creativity was supposed to be, I think probably of those 3, was the most correlated with this reasoning capability you're describing. We see a negative correlation between Gemini 2.5 Deep Think's scores and background and execution, meaning the higher the background rating, the more difficult, the worse Gemini scored. No correlation with the creativity rating.
Oh, interesting.
Which was fun. This was like a nice result, which I think like captured, I mean, there's a bit of a selection bias. Like I like this result because I think it captures exactly the phenomenon you're saying. Even though we tried to make FrontierMath span this creativity dimension, that doesn't seem to be what the models are actually picking up on in terms of what problems they find harder to solve.
Do you see the same correlation with other models?
Yeah.
Okay. I'm just wondering, because I think somehow Gemini seems to do less like synthetic data. So I think it may be my sense overall is that Gemini knows less about fancy topics.
At least same pattern for GPT-5 and others that we've looked at, which is is cool. But yes, so yes, indeed, it's missing this piece.
Yeah. So So I think the models are somehow benchmarks are somehow measuring reasoning ability less in models than they are in humans.
Yep.
The other thing is we try to write like a hard problem when one writes a problem for FrontierMath, but like realistically, the people doing this are busy. They write something that like they sort of already know how to do.
Yeah.
And a problem that a random person X already knows how to do is obviously accessible via existing techniques.
Yeah.
Maybe they haven't they came up with some new technique to solve the problem. They haven't yet put it in their paper.
Right.
Whether it's really new or just new to them is a question.
Yep.
Eventually the paper comes out and makes it into training data, and then we're no longer measuring models' ability to develop new techniques. Sometimes the hard thing that needs to be done is you need to plug some numbers into a formula where that formula is in a paper where understanding the words in that paper requires a lot of background. But okay, the models have a lot of background. They can go to a paper and plug in numbers into a formula in that paper.
Right.
Yeah. So, sometimes you end up testing things like, can you read a PDF?
Right.
Yeah.
Totally.
Yeah. So my sense is that like if a benchmark is constrained by what a person can do in a few hours, it's probably going to be saturated soon, just because what a person can do in a few hours is very limited. Like,
I do think one of the FrontierMath tier 4 contributors, and I'm blocking on his name, but had mentioned that he was quite proud of his problem because it just so happened he got, nerd sniped or whatever. And instead of just coming up with something he sort of already knew how to do, set himself a small research project.
Dan Romick, maybe?
But what he was saying is he set himself this 2-week research project, what became a 2-week research project of he set out with like, I want to do something with these techniques, but I don't exactly know how to set up what I want. And I don't think he got to like a publishable result or anything, but it was more of an exploratory process of I'm going to investigate this case and maybe a problem will fall out of it. And that sounded like a little nicer to me.
Yeah, I mean, I think, of course, the longer you get someone to spend to set a problem, I think probably that will correlate with problem quality. I do think, there's another sort of trap you can fall into here, which is like someone sets out to write a hard problem. What they end up writing is a problem which is hard for them.
Yep.
Totally. And one way that can happen is you just try to write a problem in a field where you're not an expert.
Yep.
And so
everything seems new and exciting and difficult.
You end up writing an easy problem for an expert in that field. I think, just writing a hard problem and then not trying to somehow test its hardness is a recipe for producing problems that are, or benchmarks that will be saturated easily.
So then let's get into this piece of work that Epoch is cooking up right now that we're calling provisionally our open problems benchmark. This is something we hope to release in January, just to give a sense of timescale there. The goal is to find open math problems that at least today no human knows how to solve. We're still, for practical reasons, unfortunately, constrained by automatic verifiability, excluding lean, where we want every problem, even though no human knows the answer, if an AI system were to come up with a purported answer, we could either verify it 100% or at least get very strong computational evidence that they'd hit on the solution. And there's a number of practical concerns with that, but it's meant to get around the problem of we don't know how difficult a problem is. Well, we do if people have tested it, or we have some more information. Right. I mean, I guess I'm sort of curious. I'm curious for your thoughts on all sorts of aspects of this. One I might start with is how reliable might these difficulty estimates be, and what sort of range are we going to see there?
I guess it is true that a lot of open problems are attention bottlenecked. So it could be the case that a open problem is somehow not as hard. I think one useful thing to do is just to get mathematicians to say, "Oh, I think this is hard," right?
Yeah,
because that's sort of prevents goalpost moving.
Yep.
One thing I like, by the way, about this kind of project is that, like, right now, a lot of the labs are devoting a lot of resources to try to solve some problem, so they can say we solved this problem. It would be nice if some of those resources went to problems that people actually care about.
Sure.
So it's nice to incentivize that. I think some of the labs are doing what I would consider to be real science, and some of them are primarily doing PR.
Sure.
I won't name names.
Sure.
But I think it's it would be nice to align the incentives so that more of them are doing real science.
It also feels like this at least gives us you said this, a pre-registration of a population of problems that we think it's hard to tell with a lab says, hey, our model solved this problem. Okay, how cherry-picked was that? How many failed problem solves were there?
Yeah, and so if this is something I remember, so there was this paper that came out of OpenAI, early acceleration, blah, blah. And I think they went through some conference proceedings and looked for problems. And if I remember, they maybe looked at 10 different ones they got to solve. So I think of that. That's it's a good way to explain that that they're doing that. It gives you some sense of, was this problem an easy problem, or is the model very capable? And I think, of course, if you are looking at 1,000 problems and you solve one, looking at 10 problems you solve one,
different.
Yeah. I do think I should say I don't think that paper gave good evidence that there's acceleration happening.
Sure.
And just
found one.
But
I think the denominator wasn't so ridiculous.
There are, again, as with all these stories, there's some complicating factors
totally
that make it, there's some question as to whether the problem solved was precisely the one posed, whatever.
So good. If we can get a sense of mathematicians saying, I think this would be interesting.
Yeah.
How do you characterize that? Like, what scale are we using here?
Yeah.
I know that's my job, but I'm curious.
Maybe someone, you can get someone to say, is this interesting? Is it very interesting?
Yeah.
Extremely interesting? You could get people to talk about what the consequences are, right? Like, so sometimes a problem is interesting because it is a source, right? It implies some interesting stuff. Some construction. I mean, I think the as I understand the benchmark you're proposing, you're primarily looking for some kind of construction that can be verified.
Usually, just because I wouldn't say we're looking for constructions per se. It just but we are looking
the shape of the sort of verifiable,
because we have this verifiability constraint. It's usually construct an object.
Yeah. So some constructions of this nature, like there's some constructions relevant to matrix multiplication. Which would give you a faster matrix multiplication algorithm or something. They would have genuine consequences. Maybe people care about it for that reason. I think some of these are still attention bottleneck, but whatever.
Sure.
Some questions are sinks, right? So meaning maybe they're supposed to serve as a benchmark for understanding. So
I see.
I mentioned this example of this Euler sum of Kth powers conjecture, and they're in some sense, because like a brute force search is very sort of is infeasible. That problem kind of benchmarks understanding, because you in order to solve it, you have to come up with some kind of clever search. So you've understood something about the search space.
Do you think would those sync benchmark kind of problems be fair measures of AI understanding? I'm hoping that given that they're unsolved by humans, there's not like super straightforward kind of cheat way to do it. You can't just apply the literature, find the obscure paper. Maybe we will find a couple cases.
Yeah, I think it depends a lot on the problem. Some of these things are just attention bottlenecks.
Yep.
Again, a lot of kind of constructions people look for. I think the state of the art is like someone ran a naive search on their laptop over the weekend, so you find a better construction. Like, okay, that's great. Like you tried one thing rather than 0 things. Or you tried 2 things rather than 1 thing.
Right.
I think that clearly has value doing that, but I think it's a little hard to get a sense of the what it's really showing, like what kind of difficulty. Yeah. But there's definitely some questions, like we talked about the inverse Galois problem for the magnitude group M23, where I think again, if there was a Manhattan project to solve this, it would be solved. It's like it's definitely, I think, within reach.
Yeah.
In some abstract sense.
Sure. Totally.
Not that I have an idea, but it's people have definitely tried.
Yeah.
So you get some signal from that.
I guess one question I'm sort of curious about, if it's worth considering like interestingness or value as distinct from difficulty. And like what, like I guess these correlate.
Those are absolutely different dimensions. Yeah,
I suppose they correlate because people try the interesting problems. So the interesting problems that remain unsolved happen to be hard. So there's a collider or whatever the causal term is. But like, how tightly is this correlated?
I think you've explained the source of the correlation between these two things. There are some fun examples where you see you can see something like this. So there was a recent polymath project run by Terry Tao, this equational theories project, where they were studying axioms for multiplication. So they were studying small magmas, whatever that means. So you look at all possible axioms for a multiplication rule, which ones imply which other one. So, maybe an example is x times y equals y times x. So
sure.
That's commutativity.
Yeah.
You can ask, well, what other axioms of multiplication follow from that? And so they looked at all of them up to some fixed length, and they asked which ones implied each other. And they've now resolved, maybe there were 22 million or something such computations that have now resolved all but a few of the possible implications. And so the vast majority of these were able to be solved by automated techniques.
Yep.
So I think to some extent with LLM use, but other
sure.
Primarily other computer algebra software. I mean, you're trying to manipulate some symbols.
Right. It's a lot of old-fashioned AI. Yeah. Good candidate.
And then some of them required really non-trivial ideas.
Yep.
And I think this sort of led to some I think reasonably interesting mathematics.
Sure.
Well, it's of course of this shape you're getting at. Like, if the hard problems will also be the interesting ones.
Right.
The first thing you try doesn't work, and the second thing you try doesn't work. So eventually, you get
there's something
new
here.
Technique.
Yeah.
So I think, for example, there was some notion of something called magma homology invented to resolve certain of the implications. Which to me seemed like an interesting.
Yeah, seemed neat. Yeah, totally.
There's this sort of funny thing here, which is I think if you were to ask before this project, if you were to ask like the median mathematician, is this an interesting project? They'd be like, I don't know. But I think a posteriori, it clearly is interesting in part because there ended up being some difficult implications, and then resolving them required new ideas. So, I mean, my personal feeling is actually if you go far enough in any direction, you'll get something both interesting and difficult.
Yeah.
And sometimes it's difficult because it's interesting, as you said. So you work until it's because it's interesting. You work until you get to something hard.
Right.
But sometimes it's interesting because it's difficult. Right.
Like, why is this resisting our standard techniques or whatever?
There's some interesting phenomenon here. Like maybe A doesn't imply B, but it's close to B in some way. There's some obstruction to showing it's. Yeah.
We touched on this a little before, but the goalpost moving is like an interesting thing to to grapple with. There are some cases where it sounds like, look, you didn't expect that there was a boring way to solve this problem, but looking at the AI system solution, no new ideas in sight, not within a mile. Yep. It's a grind maybe that the AI system went through. It totally proves it. It's a proof, good for it. Resolved a question we were curious about, but like doesn't seem relevant for capabilities forecasting, which is in the back of our heads, like the big bogey. Any ways we can get ahead of that? Like what are the, what's the way to do this sort of post hoc judgment responsibly? Do you have any thoughts on that?
Yeah, no, I mean, I do think I want to argue that if you're solving an open problem that is not like super attention bottleneck, and the proof is, a grind or whatever, that's okay.
Yeah.
I think you shouldn't necessarily say like this doesn't demonstrate anything.
Yeah.
Like the ability to grind is a valuable skill as a mathematician.
Sure.
Yeah, but I think you can post hoc try to categorize the solution. But yeah, I actually think solving a hard problem via grind, that's signal.
And mathematicians would do this if they could, right?
Like, right, like the should we say like the proof of the four color theorem? Well, like nobody cares because it's right. Actually, some people do say this. I think they're wrong.
That's interesting.
Yeah, and I mean, I do think somehow there's a long tradition in mathematics of goalpost moving.
Yeah.
Like if you think about a lot of the great mathematicians of the 18th or 19th century were great calculators.
Yeah.
And a lot of what they do now, any eighth grader can do with their TI-84.
Yeah.
And so now we kind of think of this kind of tabulation and calculation is not as interesting. And I think we're right to think that,
sure.
Right? We're tool users. We're allowed to use tools.
Yeah, I guess the question is, it's fair play for doing interesting math.
Yeah, for capability.
But for capability forecasting is sort of the question.
Yeah,
if we look at this and like, it's doing the same thing. The P6 on the 2024 IMO, which Alpha Proof got, like, it's shocking what a boring proof it looks like. Like it's just case.
But I think sometimes you don't know a problem is easy until you solve it.
Sure,
that happens.
Yeah,
that happens for human mathematicians too. I mean, I mentioned earlier, like last year, Aaron Lansman and I solved a 40-year-old open problem. Like we didn't publish that in Annals, and because the solution a posteriori was not that interesting. Yeah, that happens. And so I think maybe the thing to do is look at it and say, okay, we have to have some principled way of deciding whether there's a really new idea here.
Post-mortem rubric.
Yeah, you can wait 5 years and see like how many new results have been proven using these ideas. Like that's maybe an example. We talked earlier about the Kakai conjecture over finite fields. This introduced the polynomial method, which has been hugely influential. And I think so. That paper was published, I think, in Annals, and that's very well justified.
Yeah. Earned it
by the post hoc, like by the
productivity on top of it.
Exactly right. Whereas I think a grind solution to IMO P6 is nothing is going to come out of that idea.
Right. Mm-hmm. The difficulty measure here that we've sort of been thinking of, that I've been thinking of, is something like, we talked about this already, how many mathematicians for how long, maybe some notion of seniority, like a fit of mathematician for the area. Like if I said, one or two early career mathematicians tried to solve this problem and failed. Maybe they've proven that, like, whatever, they've got their PhDs, they've published some papers in the journals in their field, but not Annals or something like that. Like how big a step forward is an AI solving a problem that escaped such a team, small team or individual, from where we are now? Like, is that that's
a good question. I mean, I think it's sort of unclear to me, like how much low-hanging fruit there is of this nature in mathematics. Like, I think it's quite possible that there's a huge amount. Maybe the fact that AI systems have not already started to resolve interesting open questions
of certain level of interestingness,
a certain level is some mild evidence against this. But I think it's, in some sense, every question is a tension bottleneck, right?
Yeah,
like,
sure.
Especially in,
Manhattan problem, anything, and it gets, most of them get solved.
Yeah, I think this is quite possible, actually. In that case, that in that world, if that's correct, then I expect we'll see a huge, huge advance from AI systems. And also, somehow this benchmarking will be easy, right? Because you'll put any open problem on it, and then it will eventually be solved. That will be evidence that lots and lots of problems at that level will soon be solved. On the other hand, I think maybe there's some mild evidence that not everything is a tension bottleneck. That there's not that much low hanging fruit. Like that when people actually work on stuff, it either gets solved or it's hard.
What do you have in mind for why it feels that way? Might feel that way?
I just have in mind like the fact that it's sort of, we talked about a couple examples, like well-known open conjectures with very short proofs.
Yep.
There's very few examples.
Not so many. I see.
I think you would sort of expect in a world where we were really bad at picking up low-hanging fruit, you would expect to see some evidence that we do sometimes.
People stumble on it.
It does absolutely happen, but it's pretty rare, I think,
compared to other.
I think typically, a sort of resolution of an important conjecture doesn't just introduce a short new idea, but introduces many ideas or relies on lots of other developments in the field, and you kind of can visibly look at the resolution and see some advances required. I do think we're not always that good at seeing it. Like sometimes there's results that are sometimes you prove a result because the last thing you needed was just proven recently and finally slotted into place. Sometimes you see results where something was proven and it had been in the literature for 20 years.
And then someone realized a consequence.
Yeah, sometimes I think all of us have examples of papers that come out and we're like, oh, I knew the main idea of this thing if I had just realized. There's one of my favorite papers actually by Nises and Schinder. The main idea is like in a Math Overflow answer that someone wrote in response to a question I asked from a few years earlier, and I was kicking myself. Yeah.
That's fun.
Of course, it's so it happens. It does happen a lot. Like there clearly is some low-hanging fruit of this nature, but it's still I think there's weak evidence that it's not everything.
Good. For this benchmark, we have this kind of binding, annoying, like unnatural constraint of automatic verifiability, meaning we want a computer program to tell you whether the answer is right or not. How bad is that? And I think maybe one angle, though answer however you want, but one angle is like how correlated are the problems that admit such verification with like other dimensions?
Yeah, I mean, in principle, it's not a constraint, right? Any mathematical construction, modulo issues of incompleteness or whatever, like you could imagine accompanying with a proof that you're verified. But I think in practice, it's a real constraint because you have limited resources to get people to write code that verifies
very much
software, and maybe you don't want to ask the model for itself to write.
Those are exactly our constraints. So we're limited to more like regular old computer program can verify.
Yeah. So one constraint this gives you is like, there are a lot of fields and interesting questions which are just simply not of this nature. So I think maybe you showed me a list of problems.
Yeah.
Maybe one of them was in algebraic geometry. I think there's certainly, I think, areas of algebraic geometry where just simply no question has this nature. And same with areas of number theory, although there is a lot of beautiful computational number theory where one has a chance. I think the primary area where this limits you is interest, right? So there are things like the inverse Galois problem where one wants to make a verifiable construction and that people are very interested in it. With rare exceptions, you want to make an infinite series of constructions.
Yes.
And those are, of course, it's much harder to verify an infinite sequence.
In some cases, it seems like, well, I'm curious on vibes. One problem class I've gotten excited about is merely asking for a sort of do a zero knowledge proof of maybe you have an infinite sequence where it's like, okay, I'm not going to be able to verify that you've got something here, but do it for 297. Sure. And like that.
I think that's a great way to do it. But again, the issue is like you very quickly run into practical constraints unless you can verify extremely rapidly. Yeah. Actually, what all you're asking is for the first 5 or 10
exactly.
instances. And I think even for the inverse Galois problem, you can ask for there's infinite sequences of simple groups where you could ask for, but probably beyond the first 3 or 4, you're not practical.
Yeah.
It's I think there's very serious constraints here.
Yep.
And so what I think one hopes with a benchmark like this is that the ability to produce an example is actually a proxy for some kind of understanding, or that there's some clever search happening. And I think it's often unclear whether that's the case. Sometimes I think there are some cases where we have evidence, again, that humans have tried and kind of failed, that like we sort of know we're missing something.
Or perhaps where humans have succeeded at similar problems, there's been some insight, and otherwise nothing's come out.
Yeah, like I said, there are definitely examples of problems where every new construction requires a beautiful new idea. And if you can get another example, you hope it.
There's a beautiful new idea behind it. Yeah, exactly. I sent you a list. I was curious. I mean, both... I think we're aiming to span a difficulty range. We'd love this benchmark to be continuous so we can track progress like that. I guess our risks on the easier end are, the postdoc who wrote this paper was having a bad day when they considered this piece, and actually that's no harder than an IMO P1. In some ways, it sounds, whatever, we'll defeat this with statistics. Like, it's not so bad to find some of these. I'm also curious on the difficult end, because the math that is most interesting, most difficult, often has more abstraction to it. Often, I don't know, of the problems
that might be a more of X paradox issue, but yeah.
Sorry, say more.
Oh, I just mean right. So one way math can be difficult is it requires high reasoning effort or whatever. Yeah. Another way is that like you need to learn a lot of what a lot of words mean.
Sure.
You have to, like hold a huge kind of theory in your head. And
sure.
Yeah, and so I think it's possible that algebraic geometry maybe has a reputation of being very hard.
Yeah.
I think it's quite possible that that's just due to the fact that nothing intrinsic to the subject is that humans are kind of bad at it, and very few humans are in it at all.
Gotcha.
Yeah.
Right. Attention bottlenecks strike at all points on the space. Of the problems I send you, I was curious, like, did you have any gut of like, oh, this is like actually much harder, much more interesting?
So there are a few. Yeah. So one of the problems was the inverse Galois problem for M23. So that I think I can certify as a problem I would be very excited to see solved, even though I think it's, it's sort of within reach of a Manhattan project.
Sure.
It would be a big deal if, and I would be very excited if humans solved it. So I'd be very excited if an AI solved it. There were some problems about irrationality. So I guess in the late 70s, maybe.
That's right.
Apéry proved the irrationality of zeta of 3, so the sum of the reciprocals of the cubes of the positive integers. And it was sort of a magical proof. Like he kind of he explained the proof at, I think, this conference Journée Arithmétique, and no one could believe it. And then it's quite short actually. And went home and checked it, and it was amazing. And people later realized it was connected to some deep theory, so the theory of physical G functions. And so, as I understand, the problem is to sort of find some kind of sequences of integers, or another way of saying that, power series satisfying some properties. That would let you run this for other interesting constants.
That's right. Reapply the same style of proof.
And there's certainly, I think that's very interesting in the sense that there's certainly been some effort devoted to that. So Zagier did a lot of, Zagier, who's a very, very, very serious mathematician, did a lot of computations, like trying to find analogous sequences or power series with some mild success. Maybe there were 6 or 7 examples he found.
But none of them like things you would have picked ahead of time as like the most important or the most
I mean, he had some ideas, and then there were sort of a few other sort of there's been very recent progress in this area by Caligari, Dimitrov, and Tang, where they instead of finding new sequences, they found new ways to apply the same general method with many very beautiful innovation to let you do this with other sort of broader class of sequences. Although maybe it's not. I think it's not exactly clear to me exactly what collection of properties one needs to run this argument. It seems like there's a little bit of artisanal work that needs to be done in each case. So I think this can be certified as hard, and that a lot of people have thought about it. I think there's some kind of theoretical reasons to suspect that, like, at least the techniques that Apéry used, like there's limits in terms of how far they can be generalized.
Right. I mean, this is the another edge of another challenge we face with this benchmark is we want the ways we're posing the problems to be solvable.
Right. You're trying to ask questions which have an answer.
Yeah, exactly.
True conjectures. That's already a very hard thing to do, is to figure out what's true, let alone prove it.
Right. I'm curious, do you have a sense if one mathematician familiar with an area, otherwise respected by their colleagues, tells us that they are 80% sure that this problem resolves in this direction, though they don't know how to, they can't produce the construction themselves, how much credence do you give that?
I would say it's slightly better than random chance, but not. People change views all the time. There are a lot of examples. I think one of the examples of the problems on your list, so finding an elliptic curve of rank at least 30, for a long time, everyone in the field believed that the ranks of elliptic curves were unbounded. I think now maybe the majority of people believe that the ranks are bounded.
Oh, really?
So there's a lot of, I haven't done a poll, but
there's just
a fair amount of recent heuristic work suggesting that, although I think some people have doubts.
Fascinating.
Yeah, so I think it's, people's views of the truth, just guesses as to the truth evolve. If you ask about the Hodge conjecture, I think probably most algebraic geometers believe it, but there's a lot who do not.
And then some cases we get proofs that some construction exists, but no one's been able to.
Right.
Those are like the ideal case, but perhaps a minority.
Maybe you can
also maybe less interesting. I don't know.
No, I mean, I think I actually quite like that kind of thing. Like, for example, there's bounds on Ramsey numbers from the probabilistic methods. You can ask for explicit constructions. I think that's a very interesting question, although it's far from my area.
Yeah.
And one of the problems I'm working on now is like Sarah asked for some examples of some objects that have been constructed via very inexplicit techniques.
I see.
And I've kind of been working to find explicit constructions. I think that's a very fun thing that, I mean, it's very different to do something explicitly and inexplicitly. Like, it gives you a lot of insight. So I actually am very in favor of that kind of problem.
What are the heuristic arguments or good examples of these heuristic arguments that make people updates without actually having the full proof or like a really concrete?
Yeah, that's a good question. So I mean, there's a long history in number theory of making random models of number theoretic objects. So for example, you could think maybe the prime numbers are distributed like a random collection of integers which have you list all the properties you can think of that the prime numbers satisfy, and then you try to make a random sequence with those properties, and then ask, well, what properties does that random sequence satisfy with probability 1? And then you say, oh, maybe the same things are true of primes. You might try to you list all the properties you can think of an elliptic curve, and then you try to make a random model of an object with those properties, and you ask, what does it have? Maybe a very basic situation is maybe you have a n by m matrix that is given to you in a specific n by m matrix that comes from some geometric or arithmetic situation. And you say, well, maybe it should behave like a random n by n matrix. And so you for example, there's beautiful work by Melanie Matchett-Wood and collaborators studying random matrices of integers. And they use that to make a number of beautiful number theoretic predictions about elliptic curves and related objects. And so, yeah, I think that's the kind of heuristic people have in mind. So there's a theorem behind it. The theorem says a random object of this satisfying properties x, y, and z has such and such properties. So it has, property x with property 1. With probability 1, it has, some invariant of it has the following distribution. And then if you are getting, I don't know, maybe you have some way of producing a abelian group out of a number field. So a classic example is the class group of a number field. Well, you say maybe that behaves like a random abelian group generated according to some distribution. And then one expects that if you just list all number fields in order, number fields are objects where you can add and multiply and divide, like the rational numbers. So they're finite extensions of the rational numbers, for those who know.
We've long left the realm of defining most of the things we've.
So you expect the class groups behave if you just list them in some natural order. Like the proportion of them satisfying property x, y, or z behaves like a random group satisfying all the properties you can think of, and that's called the Cohen-Lenstra heuristics. So that's one of the driving forces behind a lot of number theory or arithmetic statistics right now. And so the heuristic is the heuristic work is you come up with a random model and prove some properties it has, and then you try to prove that the actual kind of non-random objects you care about have the same distribution or the same behavior.
If an AI system wiped the floor with this benchmark with problems of the kind that we've discussed or you've seen, I've shared with you, what sort of world do you think we're living in?
I would be very excited. First of all, I mean, presumably it would
learn something interesting.
Problems. Yeah, presumably whatever it did to find these constructions would be interesting, at least some high proportion of the time.
Yep.
I think there's a good question as to how we should expect it to correlate with other capabilities. It's not 100% clear to me. So I'm not, with these sorts of constructions, there's kind of a clear reward signal. You can kind of imagine, you can try to imagine trying to directly train a model to target this kind of construction. And it's unclear to me whether that reward signal would generalize to like proofs, for example.
Sure.
I mean, of course, one can also verify proofs. And
right. But maybe you have to wait for that machinery to be better set up before you train on it.
Yeah. I mean, I think in general, a big open question for me about the future of math capabilities is just how much generalization is happening.
Yeah.
Right. Like a world where, to get every time a new mathematical object is discovered or invented, depending on your philosophy, you need to train a new model from scratch is a very different one from a world where the models can
pick it up and run with it.
Yeah, pick it up, or even just one where like general knowledge and capability in algebraic geometry generalizes to algebraic geometry plus epsilon.
Yeah.
Right. Like we're constantly, I think I can think of kind of 10 new versions of what a space is from the last 10 years or something like that. And not even just continual learning, like if each of those requires, if you can imagine a model that learns what those are, but doesn't learn, capabilities and have the capacity to play with them the same way a human can. So, I mean, here we're talking about a very special case where we have a model that's very good at making constructions that are verifiable. I think it's an open question how much that correlates with sort of broader capability. It would clearly be like an epochal development, though. So
for math, certainly, and then for broader capabilities, it would just depend on what that system looks like in terms of its generalization. Right, where it could be extremely narrow. I mean, we've hill climbed our way to game playing. And if it's just sort of
we already see some constructions like this from AlphaEvolve. I mean, AlphaEvolve is not doing interesting proofs, it's doing interesting constructions.
And actually, just so you're on the record on Twitter with this in a thread with some Epoch folks, I think, on the interestingness, nonetheless, of the Alpha Evolve constructions is limited. I think you're.
Yeah, I would say it's primarily the specific constructions that are primarily interesting because they're, because it's an automated system doing it. But one could imagine a future iteration where the constructions themselves. I mean, I think that's what your benchmark is trying to getting at.
That's exactly right.
Where the constructions themselves are of substantial independent interest.
And the last real thing I have on my mind on this is generalization from not just to other fields of math, but it's outside of your direct area of expertise, but to scientific fields, R&D fields, like in a world where AI systems are regularly resolving interesting math problems, and let's say not through hyper-specialized methods, not a system, not alpha proof, or
AlphaEvolve.
Not alpha, not AlphaEvolve. What do you think that looks like for the sciences, for AI, R&D?
My view is that right now the primary obstructions to AI doing autonomous high-quality math research are the same as the obstructions to doing any kind of economically valuable labor. Sometimes you need to be creative, you need to adapt to new techniques, you need to learn something, you need to work on something for a long time. Those are all things that current systems have problems with. I suspect, first of all, that if those problems are solved, the models will become very good at math research. And that suggests that I also think solving those problems is more or less required for the models to become very good at math.
I think I think one interesting thing that I was talking about with someone at a foundation who may or may not fund this benchmark was what are the chances that there's an extra ingredient that makes math difficult so that this ends up being one of the last things to fall on the path to more societally transformative AI.
I think that's pretty unlikely. That said, I think it's very hard to understand what's required for good math research.
Sure.
It's some kind of introspection. I think that, there's evidence that it involves things like creativity and, working hard for a long time and that kind of stuff. It's possible that's not true. And in that case, I think, math will, might have, there might be more progress before we see other areas. I think it's very unlikely that there's an extra ingredient to mathematics. It seems to me like this is just me observing my daily life. The practice of me doing my job is not that different from the practice of other people doing their jobs. I mean, okay, there's a lot more like lying back in my couch and staring at the wall and just kind of thinking about stuff. But I think the actual ingredients are pretty much the same as any other economically valuable labor.
Very good. Are there other questions we should have asked you or things you wanted to talk about, get onto the record?
Yeah, maybe one thing I just want to, we touched on it a little bit, but I want to talk about it a bit more is I think a big question here, and I should just say, I think I learned this point of view from Tamai, is about the marginal cost of doing different mathematical activities. So I think right now, at least where I expect AI to have a significant impact is that the marginal cost of trying something is getting very small. And that has an impact, large part because sometimes you make a conjecture. In order to check it, you should probably, have run some computer program to do some computation, and you were too lazy to do that. And a lot of conjectures have this flavor, and you don't need a very capable system to resolve that kind of conjecture. We're already seeing a lot of these things fall. I think that's a huge deal.
What sort of might not be the right concept. What sort of acceleration to math progress does that give you, or does it open up new angles, or like what do you expect?
Yeah, so I don't think of it as much about acceleration. It's just like there's some tax on progress, which is like you have to try something, and bring the cost of that down is meaningful, even if I think the primary bottlenecks are elsewhere. Like
sure.
Yeah, like you have to try something that's like that is a bottleneck for sure. It's a friction.
Yep.
I think the primary obstructions to progress are like you have to have a good idea.
Yep.
And most people have a couple of those a year.
Yep.
Not clear to me how much AI helps with that, but trying one. Sometimes you don't need a good idea.
Yeah.
And knowing when you don't need a good idea is very valuable. Like sometimes you just need to sit down and grind something out. So I think even holding capabilities constant, we should expect a lot of frictions to disappear, and that seems to me like currently to be the area where I expect the most progress to happen.
Just like even though you don't expect that to cause a discontinuity in math progress, that's the framing you find most helpful for what AI is bringing to math
right now.
Right now, cool.
Yeah, I think in terms of acceleration or whatever, I would really love to see some kind of way of operationalizing that and actually measuring, like, are we actually seeing acceleration? Like, have we ever seen acceleration is kind of an open question to me.
Totally.
Like has the productivity per person of mathematical work increased with time? It's just not clear to me, even though we have all these sort of new tools. If you look at like how do you operationalize that question? Like, you can look at citations, I guess. Like it's not it's a sort of obviously very bad proxy. It also seems to correlate relatively well with population.
Before we wrap up, any things you're looking for in the next couple of months, I don't know, that would be interesting? Anything short term that we
what I would say is so I think in August maybe I said something like it's weird that we haven't seen a lot of mildly interesting conjectures resolved by AI. Given the capabilities of current systems, so mildly interesting but attention bottleneck things. Yeah. I guess we're now starting to see those, arguably. I would expect, within the next year, we'll see a lot of those. So a lot of, problems that no one has really thought much about, trying to throw away questions, but things that people found interesting enough to write down, resolved autonomously. That seems quite likely.
All right, we will have plenty of opportunities for emergency podcasts in the future. Everyone follow Daniel on Twitter. It's honestly a pretty good source as these things go of AI math news writ large, for better or for worse. But yeah, we appreciate it. Thank you so much for talking with us today.
Thank you so much for the invitation. Yeah, it was great. Great to be here.
Very nice.